In the final part of this video, I'm going to be looking at addition reactions. And I will be talking about two specific reactions that you might not be familiar with, called the Michael addition and the Robinson annulation. And again, it's based on chapter 2 of Smith's organic synthesis and the section on Michael addition and Robinson annulation in chapter 9. And you have copies, it's available through the Noble database, and you have links to these resources on the Blackboard for the module. This is how an addition reaction looks like. It's the addition of a, of a compound to your double bond. This is just a specific example of how you can add bromidric acid or hydrogen bromides to a cyclohexene. And as you can see, the first step is the attack of the double bond on the hydrogen part of the hydrogen bromide, and the liberation of the bromine anion, and the formation of a carbocation, and then the attack of the bromine to form the addition, to obtain the bromine, the substitute with the bromine atom. Addition of hydrochloric acid or bromidric acid or iodidric acid, the substituted alkenes, lead to the anical halide, where the nucleophile, your bromine, your chlorine, your iodine, is attached to the more substituted carbon. So if you have, for example, here, you have a double bond in which the more substituted of those two carbons is this one. And that is where the bromine, in this case, the bromine atom is going to go. And we call this a Markovnikov addition. And the reason for that is because the intermediate of reaction is a carbocation, and the most stable carbocation will form. And in this case, the carbocation will form here because this is a tertiary carbocation and is the more stable one. So when the bromine attacks, it will attack this carbon, and you will have the bromine atom in the carbon that had the most substituents. You can have an anti-Markovnikov addition, but in order to do that, that means the substitution happens in the least substituted carbon. But for that, you need to have a mechanism which avoids forming a carbocation. And the way to do that, for example, is going through radicals. And this, for example, is an example of methyl cyclohexene with hydrogen bromide, but in the presence of a radical initiator, AIBN. And in this case, the reaction does not go through a carbocation, it goes through the formation of a radical. And the bromine is added first. If you compare that with the previous example, the first one to be added was the hydrogen. In this case is the bromine, and it enters in this carbon because that will form the most stable carbocation, the most stable radical, sorry, the one in that carbon group. And then, well, the addition of the hydrogen will produce the final compound, in which you have an anti-Markovnikov addition. This method, for example, is exclusive to the formation of brominated compounds, so it's not the most common one. But you can, if you choose the conditions right, you can produce anti-Markovnikov additions in which the halogen, in this case the bromine atom, will go to the least substituted carbon in the double bond. The addition of halogens X2, Cl2 or Br2, is diester specific. And that is because you form these intermediate, which are called a halonium ion. So then in the first step, the double bond attacks one of the chlorine atoms, and that eliminates the other chlorine atoms, and you end up with this halonium ion. And then the next chlorine atom attacks and breaks that structure. So then you end up with both halogens pointing in different directions. And for example, here, if you see in this example with bromine, you end up with two bromines in adjacent carbons, but pointing towards different directions. Sometimes you can use halonium ions not to have a disubstituted halogen compound, but to form other compounds. And for example, this is an example of formation of a lactone. And it is the first step, for example, you use iodine and sodium bicarbonate. And the first step is the addition of the iodine to the double bond. But then the next step is not the attack of the other iodine, and it is because you have a nucleophile in your structure. You can actually, this oxygen can attack and displace the iodine atom, and you form a lactone. So you can sometimes, when you have sections of the molecule that are possible to cycle and nucleophiles in the structure near the double bond that allows you to form a cycle, it is possible to form other compounds rather than just the double addition of the two halogen atoms to the double bond. When you have a conjugated ketone, an aldehyde, or an ester, which is a ketone, an aldehyde, and an ester with a conjugated carbon-carbon double bond, you can have something called the Michael addition. And in the Michael addition, as you can see here, the nucleophile attacks the carbon that breaks the double bond, and you end up with this sort of intermediate, resonant form of the enolate form of the intermediate of reaction that then, it protonates to form the ketone with the nucleophile in this position. So this is an interesting way in which you can add a nucleophile in a beta position with respect to your carbonyl group. And another example of this reaction with conjugated ketones is the Robinson annulation. And that is when you add a conjugated ketone to another ketone, and you can actually form a cycle. And now I'm going to ask you to stop the video and have a try, see if you could come up with a reaction mechanism for this reaction. Cyclohexanone and this conjugated ketone to form this cycle. And as a tip, as a tip of what you're going to form, this carbonyl group is actually this one. So keep that in mind. The carbonyl group in the final structure is the carbonyl group that comes from the conjugated ketone, and the double bond is formed by elimination of this carbonyl group. So stop the video now and just try and see if you can come up with a possible structure. So I hope you had a go at trying for a mechanism for the Robinson annulation. It's not very straightforward. It can be quite confusing at the beginning, and it's all based on playing with the keto and enol forms of both ketones, both the cyclohexanone and the conjugated ketone. So the first step is to form the enol form of the cyclohexanone by using a base. And let's say one of these hydrogens here that produces a movement of electrons, and the enol form of the cyclohexanone is formed. And it will be that enol form that reacts with the conjugated ketone, your other fragment of the molecule. So if I draw here the cyclohexanon in our enol form and I make it react with the conjugated ketone, the double bond reforms. This carbon-carbon double bond attacks this carbon-carbon double bond, and there's a movement of the electrons in that part of the molecule. And now you have reformed the carbonyl group of the cyclohexanon, and now you have the other fragment of the molecule attached to the cyclohexanon. So they are both together. And now we're going to try to make the second cycle, the second 6-member ring. So the next step is with some of the protonated base, reforming the ketone form in this part of the molecule and producing the cyclohexanon. It hasn't changed. The carbonyl group has reformed in this part, and this hydrogen has protonated. The next step is reforming the enol form of the ketone, but instead of on this side of the molecule, we're going to reform it here. So we're going to be looking at one of these 3 hydrogens of this methyl group. So again, we use the base. We capture a hydrogen that moves the electrons across the molecule, and we form this compound. Now we have an enol form, but the double bond is on the other side, and the other carbon adjacent to the carbon with the oxygen. And it's going to be this carbon here, which is going to attack this the carbonyl group from the cyclohexanon fragment. And at the moment, the way I drew it, they are quite separated. But if I draw it in a slightly different way, so they are closer together, hopefully you will see how the second 6-member ring forms. So I'm going to draw it like this. And I'm going to put the oxygen here and the double bond here. And now hopefully you can see how that 6-member ring forms by reforming this carbonyl group and this carbon in the end attacking the carbonyl group of what used to be the cyclohexanon, and finally forming the 2 6-member rings. Your oxygen becomes negatively charged. You have formed a second 6-member ring, and the carbonyl group, this one here, is the one that is here. Then you just simply protonate this oxygen to make the alcohol. Again, I draw the 6-member rings. I draw the ketone, which is here, and I draw the OH here. And then by an elimination process, I end up forming the double bond in this carbon here, and I produce the final product, which is the 2 fused 6-member rings with the ketone here and a double bond between those 2 carbons. So a conjugated ketone in a fused in 2 fused 6-member rings. So this is all. Thank you very much for watching, and I hope it was useful. And if you have any questions, please do email me and let me know. Thank you for watching.